Hey folks, how's it going? So I just was something I just wanted to try here, and it has to do with the flat Earth and compared to the globe Earth, and it has to do with the angle to the stars. Now, as we know, we can go out and prove. Would go out and prove it right now, but if it wasn't cloudy, is the angle to Polaris. And I have an equatorial mount telescope, and if I could set it at the latitude I'm at, then I know for a fact that I'll point to the Polaris. And it is about 53 degrees latitude, I think about there. And if I put that out, I will point my line my equatorial mount up, like towards the Polaris star. I'll look inside my telescope and I'll have Polaris dead smack dab in the middle of my viewfinder. And that's how I know that this works. Now, this could work for celestial navigation and as well as observing the sky, the night sky, for like anybody who's an astronomer, amateur astronomer, professionals, such like that. Now, one thing is we actually do know is that the angle to Polaris from the equator is 0 degrees without refraction. You know, if you count for refraction, it goes up a couple degrees, but without refraction being accounted for, it's at 0 degrees. And as you move your way up the lines of latitude, the angle of Polaris coincides about. So, you know, when you hit 45 degrees latitude, Polaris is 45 degrees in the sky, all the way up till you hit the North Pole, which looks straight up is 90 degrees. Now, the question is, compared to the flat Earth, compared to the globe Earth, what works? Which one could work? So let's have a look and see. So, I've got some measurements here that I've done, and I've done 90 degrees. Sorry about this, something's on my countertop. That's for Polaris. Now, if we go down to 62.5 degrees, now it kind of works. You can say it's like that because flat earthers claim that the stars are local; they're in some sort of magical dome. But if you go to 52 degrees, as you notice, something kind of, So let me just get my protractor out here so that nobody can say I don't have it. So we're at 62 degrees in the year, so about 62.5 degrees. And then if we go down to 52 degrees, so 52 degrees, as you can see, these two lines seem to be kind of looking different place compared to here. So this is already starting to be a problem here for like any kind of celestial navigation. We're talking people are getting lost here, right? As well as me, like if I set my equatorial mount and the Earth is flat, suddenly this wouldn't work. Say 52 degrees, here we are. That's about where I'm at. I'm at 53 though. I'm at 52 degrees. And as you can see, that takes off a different way. Then if we go 45 degrees, then we set at 45 right there. So this line takes off. It's going kind of a different way. Now really what happens, you go south of 45, 22.5, about half of that. And oh my, I mean, if you're celestial navigation, where are you looking? At 22.5. There you are right there. Well, hold on, let's look way off here. Now, 90 degrees for Polaris is up here, so what's that doing off there? There we go to halfway, so 11.25 degrees. 11.25 degrees. We're way off over here. How does this work? Then, obviously, equator, 0 degrees. So, how is the star up here, flat Earth, but it's also here, 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 and here, all at the same time? This is only going halfway down, right? The flat Earth obviously goes way out, and you should be able to see Polaris still. If it's way up here, and this is the flat Earth, then you go here and you can still see it up there, but you can't. And you get the southern star trails, then you gotta look the opposite way, which why would you have to do it on flat Earth if it's flat? Now let's look at the globe model. So here's a globe. Now the globe model seems to work. So here we are. Now this one here, I kind of did some random ones here. So we got the first one here at 25 degrees. Obviously, here's the equator. 0 degrees. That seems to work because you're looking at 0 degrees over the Earth. If you're standing here, 0 degrees straight up. Okay, well that works. 25 degrees. Now let's see if that works. Let's go 25 degrees. We're standing on the Earth. We're going to line that up. I want you to look at that right there, 25 degrees. Well, that works. So let's try our next one, right? These are the lines of latitude. So we're going to go 45 degrees, right? 45 degrees. Now let's see if I go onto the, looking at from the surface, line it up and touch it there, and there you are. 45 degrees. Let's see if we can get, see, I want this line touching the Earth right where we want it. Okay, so we are, and look at that, 45 degrees. So far so good. I mean, they're all, and look, they're all looking the same way. Now remember, globes is Polaris is a number of light years away. It's very, very far away. These lines would eventually converge, but they're going to go very, very, you know, it's going to take a while. One thing is, they're all looking the same way, unlike the flat Earth. So let's keep looking here. So now we're going to look at 60 degrees. And we can go on to the, see if we're standing on the flat Earth, on the, not flat Earth, the globe. And 60 degrees, looks lines right up. And we'll go again. At 75 degrees. So we're going to stand on the Earth. We're going to look up, make sure it stays touching where it should be, and 75 degrees. Holy moly! And obviously Polaris works at the North Pole at 90 degrees. Not a problem. See, there we are, touching. Both those lines are touching like that, and 90 degrees. So, globe Earth, all looking the same way. All the angles work, match out, all even. Flat Earth, if you go to those lines of latitude, you're kind of looking all over the place. Celestial navigation would never work with this model because you wouldn't know where you're looking. If you've seen Polaris here, and you're looking up, you think you're at 62, let's say 62 degrees, but maybe you're actually at 22.5 degrees. You're looking here, but you see Polaris up there. So you're completely wrong. You're on the opposite side of 45 degrees. Celestial navigation doesn't work on flat Earth whatsoever. I'll show you something. So let's take the flat Earth. We're going to even out all the angles. We're going to make all the angles even. Okay, so we're going to try it a different way. All right. So there you go. All the angles, all nice and even. But hold on, wait a minute here. As you go, distances get further and further and further apart. And obviously there's 0 degrees. Now how do you get 0 degrees on here to the to Polaris? If we have Polaris sitting in one spot, we have all the angles, but yet it seems to not work out so well. Because as you go along, the distances get further and further. Now we know that the you move 60 degrees nautical degrees or 69 miles, that the angle of Polaris drops by 1 degree. But if we move here, move 1 degree each, or actually 10 degrees, so it's 10 degrees. But you see 10 degrees, we should actually have equal, there's equal there. So these distances should be equal. And as you can see here, we'll measure it. So it goes from 0 to 3, 3 to 6, 6. Now you think we should go into the 3, right? 6, 7, 8, 9. Hold on, wait a minute. 9. That doesn't work. Let's go where 6 was. Hold on, wait a minute. 6. 4.5. Or actually not quite. 3. So you got 3 3/4. 8 3/4. Hold on. That's a big jump. Hold on, now the next line goes from, now we're going to 6.5. Hold on. Wow. So you wouldn't be able to map this out because your distances, as the further you go from Polaris, they get further and further and further away. And so you wouldn't be able to, so every 60 miles you'd be getting less, and your angles would be off because you'd be in between there. Or in this case here, say 660 miles, or 600 miles, let's say 600 nautical miles with your 10s, you would actually be not where you want to be. So it doesn't work at all. So as you can see from that, celestial navigation would not work on flat Earth, because just measuring angle to like Polaris or any kind of constant star, like you can say use Vega, or because you can't see Polaris, or if you're in the Southern Hemisphere, you want to use Crux or Sigma Octantis, because you can't see Polaris in there because, well, the Earth is in the way, in reality, because the Earth is a globe. But as you can see there, trying either way on flat Earth, it doesn't work. Either one, your distances, as you're getting further away from Polaris, your distance is getting further and further. And if we know for a fact the celestial navigation, it's 1 degree per 60 miles, nautical miles, or 69 miles on Earth. Nautical miles measure a little different. Or if you did actually have for you were on your lines of latitude, then your angle to Polaris would be completely off, and you wouldn't be able to actually triangulate where you are, because the angles where you should be seeing it, you're not seeing it because it's way down. And obviously you get down to the equator, or right around the equator, then you're really lost, because you can't, flat Earth, so the Polaris is supposed to be up in the sky, and yet in reality we see it at like 0 degrees or just slightly above 1 or 2 degrees, and when you go south of the equator you can't see it at all. So that there completely debunks and falsifies flat Earth. Sorry, flat earthers, but there's more proof there. This is quite easy. You can stand in your kitchen, as I have, and figure it out for yourself. What works, what doesn't work. It's quite obvious to see. Thanks for watching, and see you again.
I think I will be getting a fresh supply of flerf tears soon.
Ah, yes. The good stuff. Always sweeten my coffee with the tears of flerfs.